Good afternoon, everyone. I'm Boan Tao from the University of Edinburgh. My presentation today is Smart Automatic Mixed Reality-Based Construction Inspection Framework. So the motivation behind this project is the increasing complexity and scale of the modern project. The traditional inspection mainly rely on the manual check and a 2D blueprint, which cannot detect issue promptly. The advent of digital tools such like a digital twin, building information model, artificial intelligence have improved the process. However, they also bring the new challenges like the need for substantial computation power, the need for advanced data management, and also the specific skill training in the digital practice. So our project propose an autonomous inspection system. That is, the user wear mixed reality glasses to do the inspection work autonomously. Moreover, the user can real time check the inspection results on the screen and also digital twin. So let's first look at the first step. Oh, sorry. The components, the proposed system comprise two primary components. The first one is the mixed reality devices, which specifically choosing as the Holland 2. Another one is the computation center, which can be a local computer or cloud platform. Let's look at the first step. Detection zone analysis. The system first evaluates whether the user is within the detection zone. Detection zone are predefined area in the BIM model where specific object need to be inspected or monitored. So it can be several rules in the building, like in the first fixture, the green and the red area. And also it can be several area in one room, like in the second figure, 4 different color represent the 4 different detection zones. So if the user is within the detection zone, the computation center send activation command to the HoloLens 2. The HoloLens 2 start capture a video frame and send all this information back to the computer center. Object detector runs in real time on this capture video frame. In this project, we focus on the switch and the socket. It can also adapt to other objects. So we develop a deep learning model based on ULOE5, known for its rapid and precise performance. The initial pose of the device is obtained by scanning QR code, and its position and orientation is updating in real time. Then the system using this information to check to do the orientation validation to make sure that user face the object and also the camera object incident angle is within the acceptable threshold. So that the subsequent projection and matching calculation can receive high accuracy. Here I want to say the camera object incident angle represents the angle between the camera orientation and the normal line of the surface of object. Then we do the 2D to 3D projection. We first calculate camera object incident angle for all objects in that detection zone. We select the one with the smallest angle as the primary detection target. We calculate the orthogonal distance between these objects with the camera device serve as the z value in camera coordinates. Then using the extrace matrix to transfer all these 2D coordinates into the world system. Then the projected position is compared with as planned position. The compliance is determined by predefined the threshold. So it can both visualize in the screen of the mixed reality and also in the digital twin. So I'm going to show in a video. So the user start by scanning QR code for initialization. Then the user entering the sky blue zone. Then every detect object is marked by a green bounding box and also marked as a green ball in the digital twin. Okay, the user is moving out of the zone. the user get into the green area, and the camera active again. And we can see here the user load down themselves to adjust the camera to reduce camera object incident angle for the more precise projection. So I'm going to further investigate this issue in next slide. Oops. Yes, we investigate the relationship between the camera object incident angle and the deviation. And we find that between 0 to 10, there is strong direct correlation between two. And between 0 to 5, the all deviation is below 22 centimeters, and with the mean value 17 centimeters. We also investigate the relationship between the camera object distance with the deviation. And we find that below 1.1 meter, the deviation is stable, and below 25 centimeters. So our finding that when the camera object incident angle less than 5 degrees, camera object distance less than 1.1 meter of system achieved the best performance with the mean value 16 centimeters. There are several reasons to explain the deviation. The first one is the QR code scanning, and also built-in device tracking is not precise. Maybe more robust tracking system like using the use of the beacon can improve the performance. Another reason can be the image distortion, perspective, and the lens error, lighting and shadow effect. Also, IMU sensor inside the HoloLens 2. Thank you.